much, Christoph, for the introduction. The question that we decided to put on this talk was whether robots can make more stable solar cells, whether they can help us to improve the stability. And what I'm going to go through is a series of basically development steps that we went through over the past years with a lot of people involved, a lot of colleagues, a lot of PhD students, and I'm sort of going to be summarizing the work of all of them. First, what we have in organic solar cells is always different challenges for stability. Like, of course, light stability, where just the incident light can degrade the material. This often depends on the spectrum. Then temperature can play an important role, and of course, the atmosphere. We are using these degradation chambers here to control temperature and atmosphere. And then we're using different light sources that we put on top of these degradation chambers, like LED or metal halide lamps, to control the spectrum. And on top of that, we can also use cutoff filters to really zoom into a certain regime of spectral sensitivity. And now, when using the robot technologies that we've been developing, or that Jared and Chris have been developing at HIERN together with Stefan Langner, we basically did go through a certain evolution in terms of what we were doing. We first started together with Stefan Langner to mix different OPV active layer materials together. We then drop casted films. Then we degraded those films in air and measured the photo bleaching effect. We then continued our layer approach with Perovskites, where Yi Cheng has been heading all the activities, to basically make drop cast layers from perovskites like we had done for OPV, just in a different system. And then Yi Cheng tested a lot of different combinations of active layers for perovskites, again, for the stability in this case, in particular thermal stability, but also light stability. After these experiences with the layers, we moved on to full devices. Here, Chris and Jared have been building up the Amanda ecosystem that can make solar cells, and Xiao Yan has been making a lot of different solar cells here, where they are made at different processing conditions. Then, for example, here annealing, then the absorption is recorded within the Amanda system, and then later this data is analyzed by Larry Lua, and then we are getting some predictions on the stability of these full devices. And the third step in our evolution of basically robot-assisted stability tests is that we are now going to multi-component systems where we are automatically fabricating full solar cells. But now we are not only changing process conditions, we are also changing the composition. So, for example, here we have made a quaternary system, and then we are trying to use all of the information that we've learned from different correlations and from different machine learning based predictions to then optimize those for component systems. This is work being done by Tobias Osterrieder and also Larry Lua. So I'm going to walk through those three steps in a little more detail. The first part, where we did OPV layers by drop casting. This is what really started us to go into this high throughput robot-based stability approach, where with the pipetting robot, we could make thousands of films, and we could then change the composition on all of these and degrade them under light. And then after all these films were degraded, we measured the absorption spectrum again. So we have thousands of absorption spectra, fresh and aged. We subtracted the absorption spectra from fresh to aged, so we see the loss. We also can sort of see in which region the losses are the highest. But in the first approach, we were just integrating the total absorption loss. And then based on all this data, what we could do is feed this into an algorithm and then predict new combinations that should be more stable. So basically here we are combining this high throughput approach that I've been showing here, which would be all the red dots in this diagram, together with another approach where we're doing these iterated tests of just a few samples, not thousands, but only 9 or 6, getting the results, defining the new experiments, making the samples, evaluating, and going back to sample preparation. And this basic loop where we are mainly using Bayesian optimizers is the thing that we also continue to use later then for solar cells, for processing conditions optimization, and also for composition optimization. What you can see here is that we can within a very short time screen a big parameter space of like 4 different components of different materials for their air stability pretty fast. And we can also do that with very little material, since we are only drop casting very small films. From this OPV approach, Zheng was also transferring this to the Perovskite stability approach, like I was mentioning in the beginning. Here we see the Perovskite dropcast films, and after optimizing all these compositions, Zheng could get highly stable Perovskite solar cells. And what he could also find is that in terms of thermal stability, there is a critical temperature where at low temperatures, different compositions are going to be more stable than at high temperatures, which allowed us to get much more insight and also sort of mechanistic understanding, not just high throughput testing, but also finding patterns and finding reasons for why some systems perform better under certain conditions. From there on, we basically started to look at the cells that were made with the robot-based platform, where here Jared has been developing a lot of the components. You can see here the automated spin coater that is being operated with pipetting channels. And since we have very precise control of where the drop is going to hit the cell, we can actually make fully functioning cells with only 15 microliter of solution, or 20, somewhere in that range, which is very nice since we don't need a lot of materials for making these devices, which then allowed us to make a lot of them, where we were using here the PM6Y6 system, and fabricated 50 to 100 devices under different donor acceptor ratio, different spin speeds, different annealing temperatures, always measured the IV curve and the absorption. And then, so this was done by Xiaoyan, and then Larry was basically extracting features from these absorption spectra and correlated them to device efficiency. So that now at the moment we can almost just from the absorption spectrum predict how efficient a solar cell will be. The next step was to apply the same method for stability data. So here we already had the features extracted, and we now degraded the solar cells that were processed under different conditions, and then correlated the absorption features together with the stability. And also here we could get a very good correlation. We were then moving on from this approach where we were changing the processing conditions to approaches where we are starting to change the active layer compositions. And with this pipetting robot and the automated fabrication, here we did a series of 50 to 60 different donor and acceptor combinations. And for each of these donor acceptor combinations, we tested 2 degradation conditions. One was basically to move the semi-finished cell with only the active layer, without the electrode, out into air for 30 minutes with indoor ambient light to see how it would change the performance if we processed in air. And then for another cell that was fabricated the same way, We kept everything inside the glove box and did a metal halide degradation test for 200 hours, where we degraded all the cells for 200 hours. And so now for all of these combinations, we know how sensitive they are to air and how sensitive they are to light when air is excluded all the time, which allows us to make these plots where we can basically plot the efficiency of a combination over its air stability, or the efficiency over its light stability after 200 hours. Or here in the last plot, we were plotting the light stability over the air stability. So basically, we can see which cells lost very little performance under light degradation, which is all of these cells here. And then we can also look which cells are in addition stable to processing in air. And we can basically hone down the most promising materials combinations from all the systems we've been testing. And then after having done this with 2 materials, Tobias Osterrieder has now started doing the same thing with 4 different materials, where we are now using quaternary systems instead of binary systems, and also testing then not only efficiency, but also the stability against light and stability against air, different types of conditions. And now the question is, what are we optimizing for? Because we can optimize, for example, for the absolute efficiency, we could optimize for air stability, we could optimize for light stability. And what we are starting now is to also optimize for price and the ease of synthesis. So this industrial figure of merit, it includes the performance, the stability, and the price. And basically what we can see is that with some of the more expensive materials like PM6, we can get systems that perform equally well with when considering the price, the whole IFOM. For example, with PTQ10, which is a little less efficient and a little less stable, but it's much cheaper. So in terms of figure of merit, this material also can perform pretty well for a potential product. And that would be a little outlook in the end, that with this automated fabrication of solar cells, we're now also screening new materials in a very standardized protocol, where we basically have 4 different steps that we are going through for every material, that we are also doing the same way for every material, which will then allow us to build sort of a database of all different materials tested under the same conditions. And there we are also always interested in collaborations to be testing new materials. With that, I would like to thank everyone who's been contributing to all the very nice results that I've presented, and all of you for your attention.